So we've developed a sort of a matrix algebra. And this is a powerful tool. Again, the theorem that we proved last time about particular solutions was only possible to prove because we have this algebra, manipulations, properties that you can apply in conjunction with using matrix operations. Conspicuously absent was division. There was no definition given for dividing matrices. Well, related to that, sort of a hidden missing item, is the idea of cancellation. So students are accustomed in high school algebraic settings to looking at an equation like this, for example, and canceling the m's, thus resulting in a simpler equation such as this one. Well, it turns out that this is problematic with matrix algebra. Part of the reason is that if you think about it, you go back to high school, and what is this cancellation thing? Well, really, that's a shorthand for division. And if you can't divide matrices, then it's really not clear that you can cancel in this way with matrices. So there's a temptation for students to say, oh, well, then we can only do this in situations where we can divide, and some students might already be aware of the existence of something called an inverse matrix. And certainly if a matrix is invertible, then yes, you can cancel. But it turns out that is actually more restrictive than necessary. It turns out that all that's required is for the matrix to have the uniqueness property that we've already talked about. If a matrix has the uniqueness property, then left canceling is fine. Specifically, you can cancel a matrix that appears on both sides of the equation on the left. Okay, now let me show you what goes wrong if a matrix does not have the uniqueness property. And here's an example I've prepared. Here we have a matrix. It's on the left, on both sides of the equation, same matrix. And there's a temptation to say, well, let's just cancel it. But look what happens when you do cancel it. The result of canceling would be to conclude that that matrix is equal to that matrix, which of course it isn't. Right, so you get a wrong conclusion. So even though this matrix equation works initially, I mean, this is a true statement, you can't cancel the this matrix on the left and without getting a false conclusion. Okay, so we want to worry about problems of this sort, and let's see now how it is that the uniqueness property protects us from this. Okay, so we're going to assume that our matrix M has the uniqueness property, and we're going to assume that MS is equal to MT, and then our goal will be to try to show that S is equal to T. All right. Well, if MS is equal to MT, I can multiply by a vector X on the right, and I can apply associativity and get this. And that means, note, if the two sides of this equation are equal, then they're equal to the same thing, and I can give that thing a name, and I'm going to call it V. All right. This actually is pretty much what we need to draw the conclusion that we want. We just have to be a little bit careful about how we look at it. So I'm going to do some renaming. In particular, I'm going to take SX. I'm going to rename it Y1. I'm going to take TX. I'm going to rename that Y2. That's all I've done is a renaming. Right? Okay. And now I'm going to look at this pair of equations and take a different point of view on that. I'm going to interpret that as saying that these two vectors, Y1 and Y2, are solutions to this system of equations, or this single matrix equation, if you prefer. All right. So certainly that's the case. If you were to take Y1 and Y2, either one, and plug it in, then the equation works because, of course, we already know this. So what? What does it help? How does it help us to know that these two vectors are both solutions to this matrix equation? Well, in particular, I know that M has the uniqueness property. If M has the uniqueness property, that means that when this equation has solutions, it has only one solution. It means that these seemingly two solutions are in fact the same solution. That's where we use the uniqueness property. this argument. And if y1 is equal to y2, well, let's not forget what y1 and y2 were. There's y2, there's y1, and that means that sx is equal to tx. And keep in mind this is true for all vectors x. Now, how could that be? How could we have sx equal to tx for every vector x? No matter what x is, sx is equal to tx. Well, the only possibility is if, in fact, s is equal to t. So, kind of a tricky argument there, but notice we do get the desired punchline of s equals t as desired. Oops. We assumed ms equals mt, and we showed that s equals t because of the uniqueness property. In other words, we have effectively shown that you can left cancel the m. Okay. All right, so there's a similar fact for right canceling. And again, this is something we have to worry about. You can't just just assert that you can cancel the matrix shared factor matrix on the right-hand side, both sides of the equation. That's, in high school algebra, a consequence of division. We don't have division. So, let's ask what are the terms under which we can still do that. Again, it's tempting to say, well, you can do that by multiplying on the right by the inverse matrix. And I know that not everyone listening to this recording knows what an inverse matrix is, but it turns out that we don't actually need that. We need less. There is a broader condition that allows this right cancellation. Okay. So first of all, let's see an example where right cancellation doesn't work. It's not hard to check that the arithmetic on this example is fine, right? This is a true statement. The product of matrices on the left equals the product of matrices on the right. But if you look at this shared factor on the right on both sides of the equation, if you were to cancel those as if that were okay, then look what you'd end up with. You'd end up with, again, an equation that's clearly false. Right? So this is an example of a situation in which right cancellation is not allowed. All right, so we ask, well, what is it that went wrong, and what is it about this matrix that makes it not okay to right cancel? Well, it turns out that the condition we need for right cancellation is that matrix you're canceling has to have the existence property. Okay. All right, so let's see why that is. So again, now our assertion is that you can right cancel if the matrix has the existence property. So said differently, we need to show that if the matrix has the existence property and if Sn equals Tn, we need to conclude that S equals T. Okay. Right, okay, well, so starting with this, again, we multiply by an arbitrary vector x on the right. And now let's give this shared factor here in x a name. Let's call it b. And before we move on, let's ask ourselves, what can we say about this vector b? Well, importantly, b could be any vector. B could be anything. No matter what you might want this nx to end up equaling, whatever b you might pick, you can make that happen. There is some vector x that will allow for nx to equal to b. And the reason that I know that I can make this happen is because n has the existence property. It's the fact that n has the existence property that says that no matter what b is, I can find an x that will make this happen. Right? So this nx is not just a specific vector. It could be any vector. By appropriate arrangement, we can make that anything at all. Okay, so b can be any vector. That in mind, this b, plug that in there and there, and this equation turns into this. And again, we find ourselves in the same situation. We have that SB is equal to TB, and furthermore, this is true no matter what B is. Critically here, we have already shown that B could be any vector. Right? So how could we possibly have SB equal to TB for all vectors B, no matter what B is? Well, the only possibility is if S is equal to T. All right, and again, that's what we wanted to show. Whoops, there it is. All right, so it's important. Two things are important about these observations, these theorems that we've made. One is that you have to be very careful with your matrix algebra. You can't just do in matrix algebra things that you're accustomed to doing in scalar high school algebra. Right? So in particular here, you can't just go around canceling things just because it seems familiar and comfortable. Importantly then also you have to remember what are the terms, what are the conditions under which you can. And it's a little tricky because, you know, again, it depends on whether it's on the left or the right. So if you want to right cancel, you need the existence property. And if you want to, left cancel, you need the uniqueness property. One last note, these theorems are not in the book. I'm including these because I think they're important. We're going to make use of them here and there throughout the course, and I think students should make sure to be familiar with them.